It is currently 12 AM, the dawn of a new day. And I am awake, messing around with settings in Blender, because not even the unstoppable and inevitable onward march of time will prevent me from uploading this very specific tutorial. For I have finally managed to document a relatively painless workflow to get any animation from Blender into Unreal Engine. As you can tell, I have been animating the forbidden popsicle. It looks as if it would taste of mangoes and blueberry. What we have done with this is baked this animation down into shape keys, because shape keys can be encoded into a VAT. What is a VAT? Well, I'm glad you asked. A VAT is an acronym for Vertex Animation Texture, wherein the pixels of the texture correspond to the local or world space coordinates and positions of every vertex of your animation. In this way, you are simply encoding an existing animation into a texture that can be read at runtime and is way more efficient, especially in game development, than a skeletal animation. Usually you would need an extremely expensive tool such as Houdini to accomplish this. Blender is free, and free is a really good price. To take advantage of this, all you need to do is go into Blender, the latest version preferably, go to the extensions platform and locate OpenVAT. Once this is installed and enabled, this panel will exist on the right of your screen. All you do is you set your range, you set up the coordinate space you want to encode everything into, I recommend object space, and then you are done. If your animation needs to remain in Blender, then that is all you need to do, and you can retime it through the geometry node setup that will be created upon baking. However, there are a couple extra steps that need to be followed for moving this into Unreal Engine, especially for the purposes of visual effects. What I shall do is make sure that my baked object has been selected. My target is of course the active object. My frame range has already been set to match the animation. Vertex data can remain unchanged. The deformation basis over here says start frame by default. However, a vertex animation texture by definition only affects the transformations, or the positions rather, of the vertices in a space. They cannot create or destroy new vertices, which means that your reference frame needs to be a frame in which the sum total of your object and your animation's geometry exists. So for that, I am going to locate this frame right here. 25 is an excellent reference frame, and we are going to set this to current frame. That's all that needs to happen for Unreal Engine. I recommend packing the vertex normals, setting strip vertex data, and create normal safe edges to on respectively. This way, you will get a very close match upon importing to Unreal Engine. And also, because this preserves UVs, I have already painted and baked my textures for the object so that we can set up a shader within Unreal Engine. Now that all of that's done, we are going to simply click Encode Vertex Animation Texture. Huzzah! It is done. We can disable the baked collection that we have from earlier, and we will notice we have an object that is visually identical to what we've just shown. The only difference is this entire animation is being driven by a texture. There is now a collection_VAT folder in my directory. It is named collection because I forgot to rename it. Upon clicking this, there will be 3 different files: the geometry, the texture, and a remap information file, only the first 2 of which we will be taking into Unreal Engine. In Unreal Engine, we can simply drag and drop collection FBX and collection_VAT into our scene. Import as they are. However, there are several things that we need to do to get these to work correctly. Select both and open both. In the mesh, we are going to search for and locate UVs and make sure that use full precision UVs is turned on. In the texture, we are going to look for compression, which should be right near the top, and we are going to switch this to HDR RGBA 16F. No sRGB. It might look like nothing has changed, however this is the difference between full precision and only approximate precision. Now that this is done, we can get to work on the shader. Linked in the description below is a GitHub repository managed by this add-on's creator, which will contain an Unreal Engine asset template material from which you can work. Simply migrate or drag and drop that material into your Unreal file. I have modified mine slightly, however it should look something along the lines of this. To prepare this for VFX, what we are going to do is go to the top left, and we are simply going to replace time with a dynamic parameter. This is the only thing you need to change if you want the lifetime to be relative to the particle lifetime. I've set this up with a few extra quality of life things that I can use to test this and basically instance this particular shader all around my project. You do not need to worry about this. For the sake of getting it to work in the first place, you don't need to change anything in this shader whatsoever, but for visual effects, this is absolutely necessary, or it can be replaced with a particle relative time node, which effectively outputs a value of 0 at particle birth and 1 at particle death. I like using this one, however, because I can retime it manually within the Niagara visual effects system. I'm going to collect all of my assets and paste them into the folder, and then all I shall do is add these into the shader before they go into the final output. Everything here can be changed, however, I recommend not touching the OpenVAT OS normal and OpenVAT world position offset nodes. With the exception of these, it is absolutely fair game, go change anything else. Now creating this has effectively created a master material, however to change the settings, just to have it be a little bit more user-friendly, we are going to instantiate this. Once instantiated, the way you interact with the shader is a lot different. This is now very important. Back in that previous folder, there was a collection remap_info. You can open this with your notepad or any text viewer, and within it you will find a series of numbers. Remap values as well as the total frame count of this animation. These values are extremely important because normalized values can only go from 0 to 1, and you cannot encode a negative number into an image. Therefore, this remaps the entire frame range so that it can be read losslessly and without needing to go through more complicated calculations. All you do in this case is you insert the VAT texture into this over here, make sure to set everything up, and then just make sure that all of these options, specifically the global vector parameters for min and max values over here, perfectly match that number sheet. Once that's done, at the top over here, we are going to simply enable all of these. Frame start will be 1, frame count will be 80 FPS. I recommend keeping at a low value for viewing. However, for normalized animations, such as the type you would use in Unreal's Niagara, you would make this FPS actually match the total frame count. So I would make this 80 because in reality, we're not going to be playing it in real time. We're going to be playing it along a curve. The last thing we will change is the resolution. So we will go here into imported, and over here on the top right you can see 1024 by 2048. That Y value is what we need. So Y resolution is 2048. And then once the VAT texture has been inserted, you'll see that your system has absolutely broken. The reason it has done this is because it is applying these transforms to the default viewing sphere. So what we do is we just simply click on our mesh and then click over here on the bottom right of this folder. Should you run into errors like I did, simply re-export the same thing but change the file type from EXR16 to EXR32, which I believe is full precision, until ultimately I'm left with this. This will now loop infinitely, which is not what I want, so I'm going to disable debug time in my particular case and enable use dynamic parameter. In my Niagara system, I will change the system type from infinite to once, press E to bring up the emitters, and then just add a minimal using the button on the bottom left. Delete sprite renderer, and we are going to add a mesh renderer. Under meshes, simply drag and drop the collection. Since we've added the material directly to that geometry, we don't need to override it here. However, we do need to first spawn a burst. There it is, and then it disappears once the shader kicks in, and under particle update, we're going to add a dynamic material parameter. Because I've set this up, the only one I need is phase. We're going to change this to float from curve, and we are going to go from 0 to 1. And now we have our whole animation. Because this isn't how I want this to behave, what I'm going to do is just reset phase really quickly, and I'm going to determine what values each pose, or state rather, is. So by scrubbing through this, 0 to 0.32 is the shockwave, and then the rest of it is the dissolve. So float from curve, we are going to go 0.32, and then at the end we are going to go 1. Middle mouse click to add a new key. We're going to make this one 0 at 0. I'm going to drag the 0.32 value across so it is near the end of the lifetime because I want it to happen just before it erodes completely. So we're going to go for about 0.5. We're going to add another key, 0.32, and we are going to hold this until 0.7, and then the rest of the time it will disappear. You will notice that at a value of exactly 0, there is actually no geometry whatsoever. We can fix this by just dragging up slightly on this value axis. 0.01 is literally enough to do the trick. And same at the end, where instead of reaching 1, we are going to reach 0.99. One thing I would like to do as well is I want the spike to appear and then disappear at the end. So what I'm going to do is under particle update is I find set new or existing parameter directly, and I'm going to add in position. simulation position is over here, I'm going to find add vector to position. Under position over here, we are just going to look for simulation position over here. This is basically localizing it at 0, 0, and then we can transform it dynamically from there. Switch this to a vector from curve. Under all of these, I'm going to keep these all at 0, so I can just get rid of that key data. The only one I want is Z. At 0, I want this very far down, and at 1, I want it exactly where it is. So we're going to go very early on to about 0.3. Control A to select everything and F to frame, and then 0 we are going to set to -1. Control A once again to select everything, F to frame, 1 to turn them into tangents, or Control W for weighted tangents. And now I can set the speed with which this shoots up into the scene. To see this more effectively, I'm going to click on Show Floor under the details here, and I'm going to increase the scale of the Z-axis until it is fully underground. This is about 5,000, and pressing play will result in this. And now that all of that has been done, we actually have a usable visual effect that exists and works in our world. As long as you don't forget to put this thing in local space with this checkbox over here, this is now a completely localized system that can work anywhere and at any speed you want in the world. An example of a practical use case for this would be something like a loot box, which I did yesterday as a sort of test. There you have it, proof of concept and a free $0 workflow to get any animation from Blender to Unreal Engine 5. And if you make something with this, please tag me on Twitter over at SPRWTV, that is Sparrow, and I will see you next time.